Hello and welcome back to part 3 of our ANSYS Fluent Fire Simulation series. If you're new here, don't forget to subscribe to the channel and hit the notification bell so you never miss an update. In this part, we'll continue our setup by specifying the gas mixture involved in the fire simulation. We start by going to the Materials section in the navigation pane. Under the Mixture category, you'll notice that the default mixture already includes nitrogen, oxygen, and water vapor, the primary components involved in combustion gas flows. Next, we double-click on Mixture Template to open the Create/Edit Materials panel with the mixture pre-selected. This is where we can fine-tune or expand the list of species based on our simulation needs, especially useful when tracking flue gases like carbon dioxide and vapor emitted from a car engine fire. These mixture settings are essential to correctly simulate the transport of combustion gases within the ventilated parking garage environment. Stay tuned as we move forward with defining properties and setting the right conditions for realistic fire behavior simulation. Like the video if you find it helpful, and drop any questions in the comments. Let's continue setting up our case in ANSYS Fluent. Now that we've opened the Create/Edit Materials panel with the mixture selected, it's time to add an important combustion product to our mixture, carbon dioxide. Here's how we do it. First, click on the Fluent Database button inside the Create/Edit Materials panel. This opens the Fluent Database Materials window, where all predefined materials in Fluent are stored. Make sure that fluid is selected as the material type. You'll see a list of predefined fluid materials under Fluent Fluid Materials. From this list, we select carbon dioxide, then simply click Copy. The Text User Interface (TUI) will confirm that carbon dioxide has been added to your working materials list. Finally, close the Fluent Database panel. Why are we doing this? Adding carbon dioxide is essential because it is a major flue gas released during engine fires. Together with water vapor, it helps us accurately model the behavior of combustion gases inside the parking garage. This step is especially important for post-processing, where we'll analyze how these gases move and accumulate in the structure. In the previous step, we added carbon dioxide to our materials from the Fluent database. Now it's time to actually include carbon dioxide in our mixture, so it becomes part of the species involved in the simulation. Here's what you need to do. In the Create/Edit Materials panel, make sure the material type is set to Mixture. Click the Edit button next to Mixture Species. This opens the Species panel, where we manage the chemical components in our mixture. In the available materials list, select carbon dioxide, then click the Add button. Now carbon dioxide will appear in the selected species list, meaning it's included in our gas mixture for the simulation. But wait, there's an important detail here. The order of species in the list matters. The most abundant species should be listed last to help the solver converge properly. So we'll select nitrogen in the selected species list. Click Remove. Then re-add carbon dioxide, so it appears at the bottom of the list. Click OK to finalize the species setup. Why is this important? This step ensures our simulation mixture accurately reflects real combustion gases. A mixture of oxygen, water vapor, carbon dioxide, and nitrogen, with proper composition priority. Now that we've defined the mixture and added all relevant species like carbon dioxide, vapor, nitrogen, and oxygen, it's time to set physical properties for the mixture. These are crucial for accurately simulating heat transfer, flow behavior, and radiation in a fire-driven environment. Head over to the Mixture Settings panel and adjust the following properties. Thermal conductivity. Mass-weighted mixing law. This calculates the thermal conductivity of the mixture based on the mass fraction of each species. It's suitable when temperature gradients are significant, such as in combustion scenarios, ensuring realistic heat conduction behavior. Viscosity. Mass-weighted mixing law. This method blends the viscosities of individual species based on their mass contributions to the mixture. It's ideal for multi-species flows where different gases contribute differently to the flow resistance. Absorption coefficient. WSGGM domain-based. We're using the weighted sum of gray gases model, WSGGM, for radiation modeling, and this setting enables domain-based calculation of how gases absorb radiation. It's especially effective for participating media like combustion gases, carbon dioxide and vapor, which play a significant role in thermal radiation. Once these values are set, don't forget to click Change/Create to apply them. These settings ensure our solver treats the fluid mixture accurately, both thermally and optically, which is essential for simulating fire and heat spread in a confined space. In this step, we modified the default solid material, which was originally aluminum, and replaced it with concrete to better represent the thermal behavior of the solid walls or floors in fire or heat transfer simulations. Here's what we did. Selected solid under material type. Changed the name and chemical formula from aluminum to concrete. Updated the material properties as follows. Density, 2,400 kilograms per cubic meter. Specific heat capacity, CP 1000J/kgK. Thermal conductivity, 2.1 W/mK. Absorption coefficient, 0.1/m. Clicked on Change/Create. When prompted whether to overwrite the existing aluminum material, we selected No. This way, the original aluminum material is preserved, and a new concrete material is added. This step is crucial when simulating thermal interactions between fluid flow and solid structures, especially in cases like garage fire simulations or heat conduction through walls. In this part, we focused on defining materials in ANSYS Fluent. We selected and customized the fluid mixture by adding carbon dioxide to the species list. We adjusted the thermal conductivity, viscosity, and absorption coefficient using appropriate mixing laws. We modified the default solid material, aluminum, and created a new solid material named concrete with realistic thermal properties. These steps are essential to ensure accurate thermal and species modeling for simulation cases involving heat transfer, radiation, and fluid-solid interaction. In the next part, we will move on to defining cell zone conditions, boundary conditions. So make sure to like this video, subscribe to the channel, and hit the bell icon to stay updated. On this channel, we regularly share step-by-step tutorials for ANSYS Fluent simulations and practical CFD analysis workflows to help you master engineering simulations. Thanks for watching, and see you in part 4.